Enough to me? Okay, now we're ready?
I'm gonna do my little intro here.
Okay, cool.
Okay, great. Can everybody see my slides?
Yeah, I see them.
Great, awesome. Okay, welcome everybody. I'm Allie Lewis, coordinator with the Vermont Ag Water Quality Partnership. Thank you so much for joining us today, and thank you to Matt Vaughan, chief scientist with the Lake Champlain Basin program, here to share with us about legacy phosphorus and potential water quality impacts from the July 2023 flooding. I wanted to share a friendly reminder with everybody about the partnership, that we have a collective vision that Vermont will be populated with farms that are vibrant, robust, and steward the land in a sustainable way that improves water quality as well as wildlife habitat for the benefit of farms, connected ecosystems, the public, and general good of Vermont. And that our purpose and mission is that we're going to work together by coordinating partner efforts to improve ag water quality, and we're going to provide education, technical, and financial assistance to the farming community. And our three main overarching goals is that we're going to improve water quality and wildlife habitat on all engaged farmland owner and operators' properties. We will deliver technical and financial assistance in an efficient and effective way, and also provide the best service experience possible for the landowner. So with that, I'm going to hand it over to Matt. Thank you so much for joining us.
Hey, thank you. Yeah, thanks for the invitation to present today. And great to see everyone's names here. A lot of familiar names on the call. Thanks so much for joining. I'm going to try to share my screen. And share. And then I'm going to do this. How does that look?
Looks great.
Okay, cool. All right. Yeah, thanks, Allie. Great to be with you all today. So I gave a 5-minute slam talk. Was that last year? About a year ago? 2 years ago? Last year? Okay, great. Time flies. Yeah, so last year, 5-minute slam talk on legacy phosphorus, and I'm happy to have left you wanting more. Allie wanted me to expand that out and talk more about legacy phosphorus, which is, of course, a huge challenge for managing Lake Champlain in our watershed here. And then Allie also let me know there was interest in learning about the water quality impacts of the July 2023 flood. Of course, it was all, everyone really experienced that firsthand, I'm sure, on the call. And I do have some things to share there and to try to put that in perspective. I was thinking about, initially, I was feeling like these are two really different topics, but when I thought about it more, they're so related in so many ways. And they're two enormous pieces of the puzzle to managing water quality for Lake Champlain. So I have a lot to cover here. Probably got too ambitious with how much I wanted to say, so I might be skipping some things, but here we go. So I'll start just with kind of an overview of phosphorus and a reminder that if we humans weren't around to change everything in our ecosystems and our environment, the only source of phosphorus to a freshwater ecosystem would be the very slow weathering of rock over geologic time. It would provide a very slow release of phosphorus into the environment. But of course, a long time ago, people figured out that adding phosphorus to crops really increases biomass. I'm sure you're all aware. And so now phosphorus is actually mined from elsewhere in the world and brought into the Lake Champlain Basin, or really brought, shipped all over the world as a mineral commodity, as fertilizer and as feed for animals. So this is a photo of a phosphate rock mine in Tunisia, just to give you a sense of part of this equation here. This is actually mined, from the earth and brought to our region still today. And I just also want to define what we mean by legacy phosphorus. And this has different definitions in different contexts and depending on where people are working. They're all right, but I'm going to use it very broadly in really kind of two ways. Well, I guess first I'll say legacy phosphorus is any phosphorus that was deposited in the past. So that includes phosphorus that's in watershed soils. So if you're a person who works with farms or farmers, you might, when you say legacy phosphorus, you're probably thinking about this, like phosphorus that was deposited and is hanging out in soils on ag fields. But if you're a lake person, so my two kiddos hanging out at the lake in Burlington here, you're a lake person or a limnologist, you're thinking about legacy phosphorus that's made its way downstream to a water body and can potentially be released. And I'm going to come back to that and explain how that process works. But legacy phosphorus, anything that was deposited in the past, and we'll talk about why it's a challenge and why it sticks around in our environment, and what it's doing for our freshwater ecosystems and around the world. So I'm going to start by giving, and I'm highlighting work from a lot of amazing colleagues here in the watershed. This is from a team at the Gund Institute at UVM. Michael Ruronen, unfortunately, has left the Basin to move. I think he's still in DC. He was part of my grad school cohort, and his dissertation was just so valuable to our understanding of legacy phosphorus in the Lake Champlain watershed. So I'm going to go over kind of the main points of his paper here, because I think it sets up the issue as to why we have a surplus, or how we have a surplus of phosphorus in our watershed. So he went back with his team to look at data back to 1925 through 2012. And I'll start with just changes in Vermont land cover over that time period. So this is in thousands of square kilometers land area, and just major categories here. And you can see that, the share of non-agricultural land increased over this time period, almost 100 years. Pasture has really decreased over this time period. Corn, some changes, but not huge changes, and that includes silage. And then hay for silage as well, or including silage, had some decreases here. So the main point is that agricultural land decreased on coverage for the Vermont portion of Lake Champlain Basin over this time period. At the same time, the amount of milk cows and other cattle changed a bit, but not that much. Okay, so we had a decrease in land area, but not huge changes in animals. And this is animal unit, so the equivalent is 1,000 pounds of animal, right? And I didn't want to show too many graphs, so I don't have a graph here, but over the same time period, milk production actually doubled. All right, so we have less land in production, about the same amount of animals, and twice as much milk being produced and being exported. And all the while, most or all of the manure from these animals is staying in the watershed. So that leads to a surplus. So here's another graph that shows each of these points is a year, and it's just showing the relationship between the density of animals and the horizontal axis here. So animals, units, so 1,000 pound of animal per hectare of area, compared to the surplus of phosphorus. So the more intense or the higher density of animals, the more surplus of phosphorus we've had over this time period. Okay. And now here's another graph kind of showing this idea. So we have the dark gray line here is a surplus phosphorus. This brown line is the feed imports, and the orange line is the fertilizer imports. So we're seeing a shift, decreases in fertilizer inputs as we have more intensive, animal production, milk production, and then increases in feed over this time period to kind of feed that more efficient system and create more than twice as much milk over this time period. And so that this imbalance has led to a surplus of phosphorus of more than 1,000 metric tons of phosphorus per year imported versus exported. And so this has resulted in an imbalance of hundreds of thousands of metric tons more phosphorus in the Lake Champlain Basin than would occur naturally. And that's just in the past, less than 100 years. So that kind of sets up why we have an imbalance because of, this is only looking at the agricultural sector, but that's where a lot of these commodities are moving back and forth across our system. So just kind of going over this, setting up this problem, we have, phosphorus surplus and accumulation, more than 1,000, 1 to 4,000 metric tons per year. And that's led to a legacy stock of hundreds of thousands of metric tons. There has been a decline in the surplus over time, partially due to a decline in fertilizer use. And they also showed an increase in fertilizer or nutrient efficiency. So the farming community has definitely become more efficient at growing crops with less fertilizer, but we still have the surplus, and that's being offset by more feed imports as well. Animal unit density, or animal unit per area, has increased by over 250%, more than double. And milk export also has doubled in this time period. And again, all this manure largely is remaining within the watershed. That's why we have the surplus overall. And another piece of this puzzle I just wanted to mention, I won't go into too much detail, is our nutrient management plans. One of the, the best tools we have for improving water quality and, maintaining business success for our farmers. It is based on, the Vermont Phosphorus Index and the, something called the modified Morgan extraction, which is kind of a measure of the phosphorus that's readily available for terrestrial or for crop plant growth, for example. So that's phosphorus that's either easily dissolved in solution or forming weak mineral complexes. So it's ready to just break off the soil and be used for plant growth. But it's not a measure of all the phosphorus in the soil. So there can be legacy phosphorus that's not reflected in those nutrient management plans. So that's an important factor here too, that we have legacy phosphorus that's more tightly bound to soil, to sediment, that's not going into these nutrient management plans, and it can be released downstream when it makes its way to a lake. So per sulfate digesting, I put this on here. It's the way to look at the actual total amount of phosphorus in a sample of soil. And the phosphorus saturation ratio is a different measure of this, and that's more indicative of what the amount of phosphorus that can be actually released downstream. I'm going to get more into how phosphorus is released down in lakes and rivers in later slides here. So this is a photo from Tropical Storm Irene. We're going to talk a lot more about flooding later in the hour, but this is just to show that, we have this buildup surplus of legacy phosphorus in the watershed, and it is running off, especially during storms and moving downstream. And then it moves into a different part of our system where it can cause problems for water quality, eutrophication, just increase in nutrients, and growth of things like cyanobacteria. So yeah, we'll come back to floods, but now we're going to look into lake processes. What is this phosphorus doing once it's in our lakes? We think about it as kind of lake bottom legacy phosphorus. And here is a crazy diagram that I'm not going to talk about, but I'm showing it just to show how complex this is between the overlying water in blue and the lake bottom sediments here. This is all the ways that phosphorus can move around and transform in our system, but I'm going to keep it way simpler. I'm going to talk about, this is a diagram of just the water in a lake. So think about Missisquoi Bay, or think about the deep part of the main lake. And down here we have the sediment where legacy phosphorus lives. And the first point is that legacy phosphorus can be released. So I alluded to this a few times. And we have several decades of, or more than a century of legacy phosphorus buildup in our sediments. Okay, and that can be released under certain chemical conditions. And of course, this, when it becomes bioavailable to things like cyanobacteria or algae, it can use this to grow along and photosynthesize, where it can access light and these nutrients. Okay, so the release of this legacy phosphorus will depend on several factors, including pH, redox potential, ultraviolet light, and physical mixing. So for that release, oxygen concentration is key, especially the oxygen right at the interface between the water and the sediment. So when the oxygen is low, then phosphorus can be desorbed and enter the water column, and then can be used by cyanobacteria to grow. Okay, so low, if you leave with one thing from this talk, low oxygen where the water meets the sediment can lead to this legacy phosphorus release. And I'll talk a little bit about the chemistry because Ali asked me to expand on all this, more than a 5-minute talk. So there's a really interesting cascade of chemical reactions. Redox chemistry, you may remember from chemistry class or environmental chemistry. So when you have low oxygen, the oxygen is reduced to H2O, right? And then you have denitrification, where nitrate is reduced to N2 gas. Then the phosphorus complexes with manganese and iron and other metals are reduced and dissolved in the phosphorus. That's the point where the phosphorus was released into the water column. And you also have manganese and ferrous ions floating around there too. And then some other things happen, but the main point is that phosphorus can be released, and we also have iron and manganese ions in the water column. Those are all indicators of legacy phosphorus release. Yeah, I'll leave it there. So, oops. So this is especially important in shallow areas, and that's because in shallow areas, you have legacy phosphorus potentially being released where it's near the surface, and cyanobacteria can access not just those released nutrients, but also sunlight, and they can photosynthesize. So they call that the photic zone of the water column, where you have the sunlight available for growth. In deep areas, on the other hand, you may have legacy phosphorus release, but it's separated from the photic zone where cyanobacteria also have sunlight. So there are things that can transfer things up and down in a water column, but generally, this is an important distinction between deep areas and shallow areas. In Lake Champlain, we have both. We have shallow bays, we have Missisquoi Bay, St. Albans Bay, and we also have deep areas. So it's almost like we have multiple lakes in one water body. There's also a disconnect in the timing of when this is important, not just deep versus shallow, but also the timing throughout a season. So in the spring, we have high external inputs of phosphorus, meaning phosphorus coming from our rivers. And that, could be legacy phosphorus from the watershed, but in this context, it's kind of like a new input, right? It's external load. And at that point, the water is cold, which is not as conducive for cyanobacteria to grow. So the timing is kind of off, even though we have these river inputs. However, later in the season, in the summer and fall, we have the warmer water temperatures, which can lead to low oxygen because things are growing and respirating in the water, using up oxygen. So that legacy phosphorus can be released. And then other conditions are also favorable for growth because cyanobacteria, like all bacteria, like warm conditions, and they especially outcompete other things, other plankton growing in the water in those hot conditions. And so this is where climate change also plays in here, because we have hot, dry periods. We can have these especially with low wind speeds, we have these extended periods where legacy phosphorus is being released and cyanobacteria have favorable conditions for growth. Now I want to show some kind of real world application of this. This is work led by Stone Environmental, funded by the Lake Champlain Basin program, also partnered with University of Vermont teams and Water Resource Services. So they're looking at, through this study, which is kind of now wrapping up this spring, they're looking at, so redox sensitive just means phosphorus that's could be released as part of these chemical reactions. So redox sensitive, able to be, more easily released phosphorus mass throughout Missisquoi Bay. So I should have said, this is a map of Missisquoi Bay. And you're seeing where the amount of phosphorus that could be released is lower in yellow and higher in red, but it's a bit misleading because even the lower range is really quite high. So this is generally, we have kind of, for Missisquoi Bay, we have high redox sensitive phosphorus throughout the bay that could be released and lead to what we call internal loading or internal release of this legacy phosphorus. So there's an estimated of about 76 to 84 metric tons of this redox sensitive or easily released phosphorus in the top 1 centimeter of sediment. The base TMDL, or total maximum daily load of phosphorus, which is an external loading again from our rivers, is 245 metric tons per year to Missisquoi Bay. And the total mass of phosphorus that's redox sensitive here in the top 10 centimeters is almost 4 times that external load, is 923 metric tons. So more realistically, about 5% of this could be released in a year, which would total 46 metric tons of internal loading. Compare that again to 245. This is a major source of phosphorus for Missisquoi Bay. And this is really what drives, along with weather conditions, really what drives cyanobacteria conditions in the bay on an annual basis. One more thing on the chemistry here, phosphorus differs from other important key nutrients in our lakes because it does not have a volatile gaseous form in the environment. So carbon can move between the atmosphere and the water and the sediment by biogeochemical processes, respiration, photosynthesis, you have carbon dioxide, oxygen, things moving up and down. For nitrogen, I mentioned nitrification, denitrification, that can move between the atmosphere and the water. These are all really important processes. But phosphorus doesn't have a gaseous form naturally in the environment. So once it's in a water body, it can be transformed kind of up and down between the sediment and the water body here through these processes we're talking about, but it cannot be lost to the atmosphere like something like carbon and nitrogen, for example. So just another key point there. I'm going to do a little climate change interlude here. I talked about it a little bit, but some of the effects of climate change, I'm sure you're familiar with, hot, dry weather. We've observed this in recent years. Reduced ice cover that makes the water surface darker earlier in the season rather than white ice or lighter colored ice, leading to more warming, more precipitation falling as rain rather than snow, and more frequent and persistent storms that we're going to talk about with the flooding portion of the talk. So these are all, my favorite word here is factors. They're all factors that can lead to challenging year for cyanobacteria or fewer bloom conditions throughout a year. But with climate change, the deck is getting stacked more against us in this category. So cyanobacteria have competitive advantages in that they float, whereas other phytoplankton trying to grow in a water column is at the whim of the water just moving around. But cyanobacteria actually can control their buoyancy. They don't have brains. They're not thinking about it, but their buoyancy is controlled by light conditions and other factors. Some species can fix nitrogen. They can actually take nitrogen and use it for growth from the atmosphere, from N2 gas. And then, of course, they thrive in hot conditions. Okay, and another important piece of work from UVM, Siim Zia and his team looked at climate change and the release of legacy phosphorus and how this is, making it more challenging to make progress in water quality. So we have this, issue of legacy phosphorus and climate change kind of stacking the deck against improvements. So this kind of the modeling that they did affirms, what I just discussed, that the effects of climate change are significant for these processes in Lake Champlain. They looked at Missisquoi Bay specifically. The TMDL reductions for external load are important and offset some of these climate change effects they found, but internal loading still needs to be addressed and is a really important process. This also highlights the importance, again, of legacy phosphorus for our watersheds, or for our lake. I'm checking the time. I think I'm going to skip the next topic. I don't know.
We
Allie,
do
what do
have
you
a
think?
couple clarifying questions.
Oh, okay, great.
Matt.
Let's do that.
Okay, so the first is, when and in what conditions do we see low oxygen in the area where water meets the lake bottom when legacy phosphorus is released?
Yeah, great question. So that's actually related to the next topic. So maybe I should dive in there. No, you know what? I'll discuss it here and I'll skip the slides. So basically, it depends on the lake, okay, and the physiographic characteristics of the lake, whether it's a deep lake or a shallow lake or a shallow area of a lake. But having a water column that is stable and not mixing is key for oxygen being depleted. So if you have mixing in windy days, say Missisquoi Bay, for example, if you have windy days, then more oxygen-rich waters from the top of the water column are mixing below, and you have less of the opportunity for and what's driving the oxygen going down is the respiration, things growing in the water and using up the oxygen. So if you have a long period of hot, dry weather, you have less of that mixing. You have warm conditions that are favorable for growth and using up that oxygen, higher oxygen demand. And you have a depletion of the oxygen at the bottom where the sediment is, where then phosphorus can be released. So I think that answers the question. And was there anything else, Allie?
Yeah, one other question.
Sure.
What makes one area more redox sensitive than another? Is it mostly water depth and oxygen levels?
Yeah, good question. So it's a few things. It is what so that mapping, I kind of skipped a few steps in that mapping and modeling, but they looked at bulk density, the type, the sediment size, basically what phosphorus is adsorbed to. So what types of complexes are being formed. So it's a whole host of factors there. And for this study, they did cores of different depths to see how much of different types of complexes are at each different soil depths or sediment depths. So, any others, Allie?
Nope, that's it. Thanks.
All right, cool. So I'm gonna skip this next topic, which has to, I was gonna talk about water density and how, mixing relates to phosphorus being, released and brought up into the water column. We can come back to that topic if we have time at the end, but I want to make sure I get through the flooding piece. So I'm going to summarize the legacy phosphorus piece here. So the big picture here is that the phosphorus that was deposited in the past creates a lag time for recovery of water quality. So we have, phosphorus that's built up in our watershed soils, and then phosphorus in the lake. There's different dynamics going on for each, but it all leads to even if we turn off the faucet now or turn off the spigot now, we have an existing problem that we need to understand and address and manage. We also are looking, so to do that, we're looking at, a mass balance of phosphorus, or understanding, doing a bit more of, what Michael Wironen study did to understand what's coming in and what's going out. We've looked at that at different scales. So the Lake Champlain Basin program funded the UVM extension. Heather Darby led this team to look at kind of a farm scale nutrient balance, to look beyond just the field and nutrient management plan and look at what's coming onto a farm and what's going off of the farm, and really focus in on managing an operation to reduce the amount of feed that needs to be imported to have a viable business, and actually improve business operations through importing less feed. So really great work, and that study is complete, and the final report's available if anyone's interested in that. And then on the watershed scale, we are currently funding a study, that one's also with Stone Environmental, to look at the mass balance of phosphorus in the Missisquoi Bay watershed. And that is a binational study. So they're looking in Quebec and Vermont portions of the watershed, and determining where, where there's imbalances of imports versus exports, to help focus our efforts to bring it back more into balance so that we can see a reduction over time of phosphorus runoff to the lake. I also mentioned in-lake treatments. So we can come back to it, but I was gonna mention the aeration system in Lake Carmi is an example of the idea is to oxygenate the water to try to prevent the low oxygen conditions where phosphorus might be released. That has had mixed success, and will likely be discontinued at some point, maybe this year, maybe in the near future. And I have slides on that if we want to come back to it. The other approach that we're looking at for a couple of water bodies in our watershed is alum treatment, it's called. So that's actually adding a chemical to the water that will bind phosphorus and precipitate it out of solution, so that the phosphorus is not available for cyanobacteria to use and grow. And I also will close this section of the talk just by saying that all this is, it is challenging to deal with legacy phosphorus, and it does not undermine our efforts for watershed restoration and for agriculture, working with our agricultural producers to reduce runoff. These are all the long-term solutions that we need to make progress in water quality. So watershed restoration is a huge piece of the puzzle, just not the focus of this talk today. So it all fits together, and we can talk more about that if anyone's interested. All right, I'm going to switch gears again to talk about the impacts of the 2023 storm in the Lake Champlain Basin. This is a historic photo from the 1927 Great Flood. The storm last year was up there in terms of its historic impact. There's some incredible photos from 1927. It really changed the landscape here in our region, and led to some really major changes in flood mitigation and community planning. And Tropical Storm Irene and the flooding last year have had similar impacts in our communities. I'll move on, or I'll kind of start this portion by showing this animation. This is just radar showing the rain that was dropped on our our region. This is the animation's over a 48-hour period. And there were a few meteorological reasons why the storm was so significant and why it just slowed down and hung over our region. I read about it from NOAA. They have some great resources there, but I don't understand it enough to really explain it. So this is just a really unique storm and how it slowed down and just dumped rain over 48 hours. So those totals range from about 3 to 9 inches over those 2 days. The highest recorded was in Calais. It was 9.2 inches over 2 days. Just absolutely amazing. The map of rainfall is here. You can see the highest, these purple colors were along the spine of the Green Mountains. And the valley also received a lot of rain, although not quite as much. And there was some in the New York portion of the Lake Champlain Basin too, but this is really a bigger event, a more historic event for the Vermont portion of our watershed. So some stats from Montpelier, the storm broke a daily rainfall record with 5.28 inches, which just sneaked past the Irene record of 5.27. The monthly rainfall record was smashed, 12.06 inches, beating the last one from August 1989 with 10.69. So obviously a really significant rainfall event. This, of course, led to widespread flooding throughout our watershed. The Winooski River, Lamoille River, and Otter Creek all reached major flood stages. This is an aerial photo from Montpelier. The normal extent of the river is part where this bridge goes from shore bank to bank here. And you can see just a level of inundation in Montpelier was really significant. And of course, there was flash flooding in smaller rivers and streams leading to impacts to our community. So obviously, there was a huge number of impacts to the storm, loss of life and property, displacement of families and businesses, wastewater damage. I don't have time to go into all of that, and I'm really going to focus on the water quality impacts, but I just wanted to acknowledge that there are some really significant impacts to our communities and heroic efforts from our first responders who are out there making sure everyone was safe during this flooding. So when we're thinking about inundation and property damage and displacement, in the short term, the most important thing to think about is how high will the river go, right? We call that stage of the river. How deep will the water be and what will be inundated, what will be underwater, what basements might be flooded, right? So if you're like me, you're glued to these NOAA forecasts for several of our major rivers. They're looking at tributary discharge or flow moving downstream, and they're looking at the rainfall forecast, and they're guessing how high the river is going to go. So that's really a valuable output of our investments we've made in water flow monitoring. These place markers or these little buttons are showing where our major tributary gauges are. So we have our eyes on water flow for a lot of our rivers. But for water quality impacts, the height of the river is less important, and we're more interested in the volume of water that's moving downstream. So that's called discharge. In cubic feet per second or cubic meters per second, the volume of water per time, because that volume of water is going to carry sediment, nutrients, and pollutants downstream. So there's a relationship between the stage of river that I'm showing here and the amount of water that's moved downstream. And so this is a graph of 19 of our tributaries all added together, representing about 3/4 of our watershed. And you can see that the peak flow to Lake Champlain was on the evening of July 11th, and it was about 110 cubic feet per second, which is an incredible amount of water. That's about just less than 4 billion gallons of water every hour entering the lake. And that's about 10 times more than what is normal for this time of year, or I guess average for this time of year. In the summer, normally it would be about 400 million gallons of water every hour, and now we're up at nearly 4 billion. So just a lot of water from this rain, not surprising. And this next one is a little bit different. It's the daily average flow from each tributary, and I've broken it up by tributary, really to show that our major rivers really drove water and nutrient delivery for this storm. The 7-day water flux, so over the week following July 10th, the top 5 rivers here, the Winooski, Lamoille and Missisquoi, Otter, and Saranac, delivered about 80% of the water volume to Lake Champlain, which is about 219 billion gallons of water. So some big numbers there. And here are some stats going back to 1990, which is when we started monitoring intensively. So the daily average on that, peak day, July 11th, it was greater than the 90th flow percentile for all of our tributaries. It was the highest ever daily flow recorded for the Lamoille River, second highest ever for the Winooski River, second to Tropical Storm Irene. And importantly, it was the highest flow ever for this date for nearly all tributaries. And that's a main point of my analysis, is that this was, a really unusual storm for this time of year. We typically see our highest flows during the springtime, and we do often get a big storm or two in the summer or fall. But this is a signature of climate change, that we're seeing really significant nutrient and water delivery in the middle of summer like this. So next I'm going to move, I should say too, these are aerial images from Peregrine Productions, who was out there with drones on July 11th and I think 12th, capturing some of these images. So next, phosphorus delivery. This is similar here. I'm showing the breakdown by tributary. And on July 11th, there was measured for the tributaries we have monitored, over 175 metric tons of phosphorus delivered. And 90% of that was from the top 5 tributaries. Again, there are different tributaries here, swapped one out, but Winooski, Missisquoi, Lamoille, Otter, and Pike delivered 90% of the phosphorus for the 7-day load here. It totals about 359 metric tons, and this is more than half of the annual phosphorus TMDL, the total maximum daily load, which is an annual budget. So this is a significant event against that annual budget. I'm going to come back to this idea and put this in context and show that storms are always when we see a sizable portion of phosphorus delivery. So I'll come back to this, but definitely a significant event for our lake. So similar to flow, I'm going to talk about some statistics for phosphorus load on July 11th. So greater than 90th percentile for all of our tributaries, the highest daily load ever for the Pike River, which is a trib to Missisquoi Bay. The second highest load ever for Winooski River, again, second to Tropical Storm Irene. Importantly, again, the highest load ever for this date for all but 2 of our tributaries. And this is interesting, it was the third largest daily load ever to Lake Champlain. So the highest ever was Tropical Storm Irene, which is probably not a surprise. And this is, again, back to 1990. The second highest was the Halloween storm of 2019. So many of you probably remember that one. Big storm at Halloween. We actually lost a part of our roof in that storm, so it's memorable for us. But this one was kind of in third place back to 1990 after those 2. All right, this is the part where I'm going to show, okay, yeah, so this is cumulative phosphorus delivered to Lake Champlain in all years since 1991. So this is a little bit different here. I'm showing, so cumulative means every line here is a year. And whenever there's a storm, you're going to see a jump up in this phosphorus delivery. So we're starting on October 1st and going through September 30th. That's what we call a water year. And we do that so the winter is not split up into 2 years. So it's like a fiscal year. We have a water year starting on October 1, going through September 30th. So this is every year here. The yellow is showing an average of all these. And this is in metric tons of phosphorus. So the highest up here is 2,000 metric tons of phosphorus. I'm highlighting 2023 here, and I only have this analyzed through the fall. So far, I'm working on redoing the analysis to kind of finalize these numbers, but you'll see what I want to point out here is we actually, and I kind of forgot about this because of all the rain throughout the summer last year, but we had a very dry early spring. So we were going into this storm with a well below average phosphorus delivery to Lake Champlain. And the storm obviously contributed a huge amount of phosphorus, and we were, brought us up to one of the highest years that we've ever seen since 1990. But comparing this to Tropical Storm Irene and the spring flooding in 2011, in 2011, we had big storms from the beginning of the water year. Again, huge spring snowmelt resulting in lake level flooding. Record over 103 feet above sea level in the spring. And then in August, late August, we had Tropical Storm Irene. So just comparing last year where we were below average and then shot above average to 2011 when we had a huge amount of loading throughout the season, throughout the year. Okay, now there's been a lot. If you follow the news at all, which you all work in agriculture, water quality, so you probably read up on the effects of the storms and what was in the media. And there was a lot of talk about how the Lamoille River delivered more phosphorus than during the storm than an entire year. And that soundbite kind of made the round. So I wanted to put that into context for this presentation. And so what I'm showing here is the ratio of a 7-day July 2023 storm phosphorus loading compared to the annual loading. So take the 7-day loading from the storm and divide it by the annual loading for each year. Okay, so what we see here is the Lamoille River in compared to 2022, the storm delivered 1.2 times that annual load, but that's really because the 2022 was kind of a low season. It was a very dry year. And if you compare it to a typical year, the Lamoille River delivered about 60%, 0.6 times a typical or median annual load for that river. And if you look at the Winooski River, it delivered about 1.3 times a typical or median annual load during that week. So huge amounts of phosphorus, especially for the Winooski River. The Lamoille River, about 60% of an annual load. And I can show you the other rivers if anyone's interested in anything in particular, but that's kind of puts it in context for what we might typically see in an annual year. And now I want to talk about or provide even more context and show that high flows are always an important time for nutrient or phosphorus delivery. And so this is a new type of plot here. So you're seeing the portion of phosphorus contributed by the Winooski River on the vertical axis from 0% to 100% or 0 to 1. And the colors here represent an amount of time for each contribution. So the biggest single day each year is shown in yellow here. And it shows that on the single biggest day each year for the Winooski River, about 5 to 10% of the total annual load is usually delivered. So a day is just 0.2% of a whole year, but the Winooski usually delivers 25 or 50 times that amount on that biggest day for the annual phosphorus load. And then if you look at the biggest 5 days, typically about 20% of load is delivered, and the biggest 30 days for the Winooski River delivers about 60% of the annual load typically. So that means the remaining 335 days delivers the remaining 40% of the phosphorus. So this is just putting this into context. Yes, 2023 July storm was a huge contributor for phosphorus, delivered more, delivered a large portion of an annual load, and storms are always important for phosphorus delivery, more so than times of base flow. And that's because the phosphorus concentration is increasing, the amount of phosphorus per water volume is increasing during a storm, and the amount of water is increasing. So they multiply together and create a disproportionate effect compared to times of low flow or base flow. All right, I'm going to summarize the second half of the talk here on the flooding piece. So we had historic rainfall amounts, 48-hour totals, 3 to 9 inches, very high river flows, greater than 90th flow percentile for all of our tributaries, daily record for Lamoille, and second place for Winooski. It was really unusual for the time of year, and this is, again, consistent with climate change trends. I can talk more about that if anyone's interested. Phosphorus delivery, the storm was preceded by a dry spring. 5 of our tributaries delivered 90% of the 7-day storm flux. More than half of the full lake annual TMDL, or total maximum daily load, was delivered in 7 days. This is a especially significant event for the main lake, and it was consistent with climate change trends in the time of year that the storm came. For this kind of abridged version of this portion, I didn't get into this, but the lake level rose about 3 feet. It went from about average level for the season to about to a record high for the time of year, but it was still not a record lake level, and it was kind of brought up to what we typically might see in the springtime. So very unusual for the summer, and it did set a record on July 23rd, I think it was, for that date, but not a record for the lake overall. And then for lake water quality, we had very high turbidity, which means low clarity. A lot of sediment in the water is very murky. You can see it here. So that probably suppressed things growing, primary productivity in the lake. Dissolved nutrients were likely available for later season growth. We had short-term bacteria impacts, but these were not widespread. They were mostly localized in a few spots at the mouths of some of our rivers. And then I'm just still working on working up the data. So this next time I give this talk, I'll likely have some updated numbers and more information on lake water quality from our monitoring. And then I also just want to point out, again, going back to what this means big picture, we do have a margin of safety with our TMDL, so it does account for some of these climate change impacts, although as I said, internal loading is also part of this puzzle. So we have a lot of challenges kind of relating to each other and complicating our restoration, which is why it's so important to understand these issues. We have a huge amount of interannual variability. So although we have this big year, like I said, last year was a dry year, a lower year for phosphorus delivery, and part of that variability, plays into how we can reduce this overall and meet our water quality goals. Climate change is a factor. Putting this back to two parts of the talk, we have climate change impacting or increasing legacy phosphorus release. We also have climate change creating more persistent, more frequent storms like this, delivering phosphorus to the lake. And then we also are looking at, our ongoing efforts to make sure that our restoration practices are being done with flood resilience in mind. A lot of our work that communities did as a result of Tropical Storm Irene held up really well last year, and areas that weren't hit as hard in Irene suffered, in some cases suffered more greatly when they were hit last year with this big flood. I nailed it, Allie. 1250. So I'm going to put this another historic photo from 1927. This is Springfield, Vermont, just showing just the power of this incredible storm. And some resources here. This is we have some information on the Lake Champlain Basin Program website on the flooding. I didn't cover it in this talk, but we had real-time high frequency monitoring going on during the flood, and you can find that data on data.lcvp.org. We have a science blog for people like you who are working in the water quality space, who are managers. This blog summarizes a lot of our research into really quick articles, so that, and it's not for the general public, it's for people who already understand basic issues and are working in the space, and we're trying to make our research more digestible for you all. And that actually, the idea for that came from a lunch and learn, I believe, about 4 years ago. So that's nice. And that's it.
Thank you so much, Matt. Folks, feel free to put questions in the chat or, raise your hand or unmute yourself, turn your video on and ask questions.
Allie, this is Sylvia. Can you hear me?
We can hear you.
Okay. My question, Matthew, I just wrote a couple of things down way at the beginning, your first 2-3 slides. By the way, incredible presentation. Very good, very informative, really appreciated, because the watersheds I work in is Lamoille and Winooski, and they were impacted. It was truly devastating to be up there late July. I did notice when you were talking about, what was the data you were collecting from? Is it since the flood, the 27 flood to 2012? Is that, what was the range that you were collecting that data from originally at your first couple of slides there? And you were talking about milk production has gone up, but yet the quantity of land, forest land has created or taken over a lot of the pasture space. And one of the things, though, I want to make sure is that crop yield is up. You were talking about twice the milk production. Well, I would dare say 2 to 3, if not 4 times the production on that same land since, 1927 or the
Yes.
early 20th century.
Yeah.
So I don't know if that factors into any of your calculations, if that's worthwhile data to be sure that it's incorporated into the other information you were using.
Yeah, Sylvia, thanks so much for your question there. And yeah, let me first clarify that for those first few slides where I was kind of introducing generally why we have a surplus, or kind of the concept of why we have the surplus of phosphorus and the land cover and the yield and all that. I was summarizing findings from a study that I was not involved with, but I can explain it and answer your question. So that was again from Michael Wironen's team. He's was on my part of my cohort at grad school at UVM. It's awesome, really awesome work. And you're describing exactly what they found in the paper. So crop yields are up, and in general, if you look at the import of fertilizer and the export of product, it's showing a huge increase in efficiency. So less land, less fertilizer, and more crop yield. So that's all part of the equation. What we're also seeing is, again, similar number of cows, but less land in production. So yes, increased efficiency, but also because it's more intensified, a greater import of feed as well. So all of it is kind of balancing against each other and resulting in what used to be a greater surplus is now the surplus, meaning the imbalance has gone down. So trending in the right direction. And it peaked in, I can show the graph again, but I'm looking here. Peaked in, I'm looking around 1950s to 1970 or so. And the surplus has gone down. So that's improvement, but there is still a surplus. The surplus is still, the paper was 2018. The surplus is still over 1,000 metric tons of phosphorus per year, but it was 4,000.
Right. And the other is that as farmers are utilizing and incorporating precision agriculture, is really going to, I think, allow or move farming practices in the state from just this general, I'm just going to spread manure all over the place, to it's going to be applied very strategically to maximize production. So
yes. Totally agree, Sylvia. Yeah, thanks for that point.
Thanks. I see Karen has her hand up.
Hi, Matt. So I'm not sure, but I'm assuming that, we know that a river is going to have a certain amount of sediment, phosphorus in the sediment, and that over the year, it's all going to be washed into the lake. So the big storms are going to wash more of it in than the other times. So would it perhaps be that the subsequent storms would carry less phosphorus in because there's less to carry in? Or are we just assuming, big rain, you're going to have the landscape that contributes more sediment, so let's not even worry about it?
Right. Yeah, good question. That comes back to like the long-term mass balance. So in general, when there's a storm, as I said, the concentration is going to go up and the amount of water is going to go up. Those multiply together, and that's why we have, the disproportionate effect of greater loading during storms. And your kind of conceptual model of if it starts, draining the watershed of phosphorus, then eventually that will go down. And that's exactly what we're trying to do with watershed practices, and to get that the mass balance in check, right? Where over the longer term, we're trying to draw down that pool of legacy phosphorus in the watershed, so that when, and not if, but when storms happen, right, and the concentration goes up and the amount of water goes up, the concentration won't be as high as it would have been, right? So that's definitely part of the puzzle, I guess.
Thank you.
Sure.
Any other questions for Matt before we wrap up?
I'll just say one more thing, and we can still take a question, but the flooding portion of the talk was an abridged version. I have more to show on that, and I think there's a recording from Vermont DC. If you want to learn more about that, and the Lake Champlain Basin Program team is working on our 2024 State of the Lake report, so that will also have interpretation and data and graphs there. That will be released on June 5th. So look out for that new version.
I see another question. Has there been any research on microplastic loading from the flood?
Yeah, good question. To my knowledge, there was no active, I don't know of any active microplastic monitoring that was going on from the flood last year. But the Lake Champlain Basin Program is funding a new study on microplastics in partnership with SUNY Plattsburgh. So that'll get underway this season. So we'll get a better idea of some of our sources of microplastics in our tributaries and wastewater treatment, and in the lake and things like that. We do have some data there, but it's a bit sparse, and that's why we're excited to learn more on that front. And I think one of the outcomes of that study is once we're able to monitor storms and tributaries for microplastics, we can kind of retroactively look at storms like last year and see and maybe estimate how much plastics or other contaminants or other things of concern might have gone downstream.
Great. And Karen, is your hand still up or is that a residual hand?
Residual.
Okay, just wanted to check.
Sounds like a disease.
Okay, I think we'll wrap up there. Thank you so much, Matt. This has been great, and thanks for everybody for joining. We did post a poll in the chat. If everybody could take, I think it takes less than a minute for you to complete, to let us know if you have any additional questions or what other topics you might want to dig in more on. You can let us know. But thank you so much.
Thank you all.